It's the most accessible and one of the most commonly used methods in industrial settings. This method has quite a few limitations. It won't detect microcracks. It's nearly impossible to eliminate all the air from a heat exchanger.
It can't predict or warn in advance. The lower the pressure, the lower the chance of detecting a leak.
Hydraulic tests simply don't reveal microcracks. The first method we'll look at is the hydraulic test. It's the most accessible and one of the most commonly used methods in industrial settings. The basic principle of this method is that one circuit of the heat exchanger is sealed, while the other is filled with water. A pump is then used to generate the required test pressure, specified on the unit's factory nameplate, which varies for each heat exchanger. The pressure is then maintained for 10 to 30 minutes, after which a visual inspection of the casing and connections is carried out to check for any signs of leakage. One of the key advantages of this method is its simplicity and accessibility. It doesn't require any complex or specialized equipment. All you need is water and the heat exchanger itself. This method allows you to check not only for leaks, but also the structural integrity of the unit. It's suitable for heat exchangers of any size. However, this method has quite a few limitations. For example, it won't detect microcracks. Water only reveals large, visible leaks. Another drawback is the labor-intensive preparation. You need to seal the circuits, fill the system with water, and remove all the air. And it's important to remember, in practice, it's nearly impossible to eliminate all the air from a heat exchanger. Since air is compressible, this can affect the accuracy of the test. This may lead to inaccurate or misleading test results. It also requires time to drain the water after the test. And for certain processes, the heat exchanger must be dried afterward, which can be critical for some types of production.
Igor, the hydraulic test is probably the most widely used one, isn't it? What's your take on it?
It is probably popular in countries and facilities where more precise, and I'd say gentler methods, are not readily available, because performing this test is relatively quick and straightforward. It doesn't require any specialized equipment, external assistance, or advanced technical expertise, which means the plant's own maintenance team can perform it independently, without delays or additional costs. This makes it especially attractive for facilities aiming to keep testing simple and fast. However, a key limitation of the hydraulic test is that it only detects obvious leaks when problems are already present. In other words, it can't predict or warn in advance that a critical leak is about to happen. Another significant drawback is that the pressure must be raised to the maximum level permitted by the manufacturer, which can create additional stress on the unit and increase the risk of causing damage during the test itself, especially if the equipment is already worn or aged. Well, to make the test meaningful, the pressure must be high enough. The lower the pressure, the lower the chance of detecting a leak.
Well, cracks that may or may not be detected by a hydraulic test can pose serious risks. Igor, based on your experience, and Sergey, I'd appreciate it if you could share your thoughts as well. What types of cracks does this method usually fail to detect, and why might that be the case?
According to the claims of suppliers who provide hydraulic testing services, this method is capable of detecting cracks with an equivalent size of approximately 50 microns or larger, meaning only relatively large defects. I say equivalent because, for comparison, they use perfectly round holes, which don't actually occur in real heat exchangers. So I prefer to say equivalent size rather than exact size.
Sergey, could you share your experience as well? How do hydraulic tests compare to other methods you've worked with?
Yes, absolutely. I agree with Igor. Because with this test, only clear and visible water leaks can be detected. For example, if water droplets actually appear, if they're on the outside like this, then you can clearly see them. But when it comes to the size of microcracks, that's a different story, especially when using a gas test. For instance, I've spoken with maintenance staff who said there was no water leakage here. But when we ran a gas test, it clearly detected a leak. That's why it becomes evident that hydraulic tests simply don't reveal microcracks. They're just not sensitive enough to pick up such small-scale damage.
Thank you. Jumping ahead a bit, Igor, I'd like to turn to you with a follow-up question. There's an issue that often arises during tightness testing. Some heat exchangers have a lower section of plates, located below the outlet pipeline. And as Sergey mentioned earlier on the slide, this creates a zone that can't be fully drained. So the question is there any testing method that allows you to check the tightness even if the heat exchanger isn't completely drained?
According to suppliers, the hydrogen test solves this issue by using a hydrogen-nitrogen mix, usually 5 to 95 or 10 to 90. Since nitrogen dissolves in water much better than helium or hydrogen, it's generally accepted that the heat exchanger doesn't need to be fully drained before testing.
Thank you.